So this would be an example on a two-sample t-test, which is a test for mean. So researchers claim that the average amount of coffee consumed by an adult per day is not equal to 32 ounces. So we collect a sample, and that sample is shown below to verify the claim. I'm going to assume all requirements are satisfied for a t-test in order to verify the claim, and the value of alpha that we use is 0.05. So I have a sample. Now, before we get to performing the test, we've got to start with the definition of the test. So mu is the average amount of the average amount of coffee an adult consumes per day, and the null is mu equals 32 ounces, and the alternative is mu not equal to 32 ounces. The value of alpha is 0.05, which would imply that the probability of error in rejecting the null has to be 5% or below. The third step, of course, is to find the statistic, and we can use the calculator to come up with the mean and the standard deviation and so forth. So I'm going to enter the data into list one and use one variable statistics to find the mean and the standard deviation. So the mean happens to be 20. The standard deviation is 14.24. And the number of observations is simply 10. Now, the average happens to be 20, and we might be tempted to say, oh, it seems like the average is not equal to 32 ounces, and we can simply reject the null and conclude that we've found evidence toward the alternative that the average is not equal to 32, but we can't do that. The reason being, we have to account for variation, which is why we need a statistical test. Based on the sample that we see, I don't think we can reject the null. Let's see if that is true. Step 4 is to recognize the distribution of the test statistic. The test statistic has a t-distribution with degrees of freedom equal to n-1, which is 9. And just because we have a two-tailed test doesn't mean we would have a different distribution. May it be a two-tailed, right-tailed, or left-tailed test, step 4 is always the same. We just have to change the degrees of freedom. There are two ways to obtain a conclusion. We could either use the critical value method or we can use the p-value method. But regardless of the method, we need to have the test statistic. The test statistic is given by the formula x bar minus mu naught divided by s over square root of n. The denominator is the standard error. Mu naught is the null value, which in our problem is 32, and x bar is simply 20. That's from step 3. So the test statistic t is 20 minus 32 divided by the standard deviation, which is 14.24 over square root of 10. So 20 minus 32 is negative 12. The standard error is 4.50. We end up getting negative 2.67 as the test statistic. Now that we have the value of the test statistic, we can go on to finding the conclusion of the test, and we could do it in one of two ways, either the critical value method or the p-value method. So with the critical value method, we have to identify the rejection region, and we identify the rejection region using the value of alpha that we have. The value of alpha that is given in the problem is 0.05. But the key difference between a right and a left-tailed test when compared to a two-tailed test is that the rejection region for those two tests would be on one side. It would be on the left-hand side for a left tail test, it'd be on the right-hand side for a right tail test. And the area that we would use to find the critical value would just be alpha. But for a two-tailed test, we would have the rejection region on both sides. Zero would be right in the middle. We will have a positive critical value on the right-hand side, a negative critical value on the left-hand side, that area is no longer alpha, rather it is alpha over 2. And it is alpha over 2 because we are doing a two-tailed test. So 0.05 divided by 2, they end up having 0.025. And we can find the critical value using inverse t. And if we don't have inverse t in the calculator, we have to make use of the t-chart. So the rejection region on the right is the shaded area, and similarly on the left is the shaded or cross-hatched region on the real number line. The notation here is t sub 1 minus alpha over 2, comma n minus 1. 1 minus alpha over 2 is the area below the critical value. Specifically positive critical value. Which in our case would be t sub 0.95, 9. Alpha is 0.05, so 0.05 over 2 is 0.025, and 1 minus 0.025 is simply 0.975. The notation on the left-hand side is t alpha over 2, comma n minus 1. Alpha over 2 is simply the area below the negative critical value, and n minus 1 is just 9. So we don't have to find both of them. If we know the one on the left-hand side, we can find the one on the right-hand side and vice versa. So go to the usual place where we would find inverse t and t CDF. Going to pick inverse t. I'm going to go for the positive side. So inverse t 0.975, comma 9. That value happens to be 2.262. Therefore, the one on the negative side would be negative 2.262. The test statistic is negative 2.67. And negative 2.67 It's probably right over there. So the test statistic falls in the rejection region. Therefore, we reject null. So I was actually wrong at the beginning, which is the purpose of a statistical test. So the p-value method is another way to obtain a solution or a conclusion. But for a left tail test, the problem from last time, the p-value was the area below the test statistic. But here we have a two-tailed test. So for a two-tailed test, the p-value is 2 times the area above the absolute value of the test statistic. We have the test statistic to be negative 2.67. The absolute value of that would be 2.67. Going to put a side note here. This is something that you should not forget. If you want to find a p-value, then we're going to make use of CDF functions in the calculator. If you want to find the critical value, we use inverse functions in the calculator. So we are looking for the area above the absolute value of the test statistic. So the absolute value of negative 2.67 is positive 2.67. And we want to find that tiny little area. And once we find that area, we have to multiply it by 2. So 2 times TCDF. We start at 2.67. We end at E99. And we plug in the degrees of freedom. In this case, it is 9. And we get a p-value of 0.0256. And that p-value is less than the alpha that we set. The alpha that we set is 0.05. Since 0.025 is definitely less than the alpha we chose, we can reject the null and conclude that we have found evidence toward the alternative. So since we rejected the null, there is evidence to support the alternative or the claim. And what is the claim? The claim is that the average amount of coffee consumed by an adult per day is not equal to 32 ounces. And we found evidence toward that. This entire process that we did can be done using the calculator. So on an exam or when you do the homework, if the data is provided, there is no need to go through all of these steps in order to come to a conclusion. But there are problems in the homework, and there could be problems on the exam where the data is not going to be provided, and you have to know the concept whether to reject the null or not reject the null. And that is the purpose of doing all this over here. In this problem, we have the data. So I'm going to make use of the data. So start, over to tests. Option number 2 is a t-test. So select 2. We have the data. So enter. Mu naught is 32 in our case. So 32. The data is in list 1, so we could leave that as is. And of the 3 options that we have to select mu not equal to mu naught, because this is a two-tail test. And, oh. It deleted my data when it turned off. So the second line is our test statistic. We have negative 2.665, which I rounded it to negative 2.67. It's right here. And the p-value is in the third line. That value happens to be 0.0258. Because of rounding, we ended up getting 0.0256. So the average amount of aspirin a senior takes per day is claimed to be greater than 100 milligrams. So that would be mu. And mu is claimed to be greater than 100 milligrams. So using that, we can construct the hypothesis. So the null would be mu less than or equal to 100 milligrams. The alternative is mu greater than 100 milligrams. So whatever you have here must match there. And keep in mind, the equal sign is always in the null hypothesis. You cannot put the equal sign in the alternative hypothesis. So alpha in this case is simply 0.01. In other words, the probability of error in rejecting the null must be 1% or less. So let's do this using the calculator first. So 50, 25, 10, 0, 200. Oops. Over to tests, pick option number 2, and we have the data. So move to mu naught. Mu naught is the claimed value, and that is 100. The data is in list 1, so we can leave it as is. And of the 3 choices that are provided to us, we have to pick the last one because the claim here, or the alternative here, is mu greater than 100 milligrams. So we just switch over to greater. And that's what we get. The test statistic is negative 1.89. The p-value is 0.95786. Let's check the data again. So 50, 25, 10, 0, 100, and 200. Okay, 150, 50, 25, 0, 150, 225. Okay. That works. So the test statistic is negative 0.7718, and the p-value is 0.7717. We have the mean and the standard deviation. So I'm just going to use the mean and standard deviation that I see in my step 3. Step 4 is simply the distribution of the test statistic. But in this case, the degrees of freedom is n minus 1, so it would be 12 minus 1. We'll have 11. The key difference between this problem and the previous problem is that the rejection region in this problem would be on the right-hand side. And why the right-hand side? It's because the test is a right-tailed test, because the claim is, or the alternative is mu greater than 100. So going to do the critical value method first. Oh no. So the rejection region is on the right-hand side. The notation here is simply T1 minus alpha, comma, the degrees of freedom. Why is it alpha and not alpha over 2? It is because we have a right-tailed test. So the area that we have up there is 0.01. So the area below 1 minus 0.01 would be 0.99. So T 0.99, comma, the degrees of freedom, which is simply 11. We could use inverse T. The area below, which is 0.99. That happens to be 2.718. So the rejection region starts at 2.718 and everything above that. The test statistic in our case, we already know its value using t-test, but manually we can find it as x bar minus mu naught divided by s over square root of n. X bar is 82.08. Mu naught is 100 divided by s, 80.41 over square root of 12. And that is pretty much the value that we got from t-test. So all we are trying to do is we are using the formula that the calculator uses to find the value using manual calculations. So the test statistic is negative 0.7720. So the test statistic is somewhere right over there. So clearly the test statistic does not fall in the rejection region. So we do not reject the null.
The rejection region is the shaded area.
Since we do not reject the null, we find no evidence toward the alternative. When we say no evidence to support the alternative, all we're saying in this case is the claim. So we did not find any evidence toward the claim. We can obtain the same conclusion by using the p-value method. The difference here is the p-value is the area above the test statistic. So for a left-tail test, the p-value is the area below. For a right-tail test, it is the area above. And for a two-tailed test, it is 2 times the area above the absolute value of the test statistic. So we still are going to use the TCDF function. So TCDF, it is the area above So in my graph here, going to start at t equals negative 0.7720, which is the test statistic, and everything above that that shaded area would be the p-value. Clearly, just by looking at that picture, we know the p-value is going to be bigger than the alpha. The alpha is in teal, it's about 0.01, and the p-value is the gray or bluish gray area. Clearly that area is bigger than the area in teal, but we could find that answer numerically. So second was TCGF. We start at negative 0.7720, which is the test statistic. We end at E99, and the degrees of freedom is 11. Enter. And we get 0.7718, which is definitely bigger than the alpha we have, so we do not reject the null. The conclusion is the same as I wrote earlier.